Hi. Hey. So, this is topic 7.2, obviously, because you're following along. And I just want to say that I'm obviously following College Board and their approach to the curriculum more than I ever have. I've never done topic 1, 2, 3, right? So I'm a little confused as to why they're doing things the way they're doing them, but I'm going to stick with it. Okay. Um, just going to stick with it and see how it goes. All right. So this video has to do with the direction of reversible reactions. Now I had to literally like try to figure out what are they talking about? What do I need to include in this? So I'm going to give it my best shot. All right. Um, Like I know what you need to know, but I don't know what they mean, direction of reversible reactions. But in looking through questions, I think I have an idea of what this topic is supposed to entail, doing a little bit of reading, looking at questions. So, all right, what do we know? We know that at equilibrium, right, we know that the rate of the forward reaction is equal to the rate of the reverse reaction. All right, we've talked about that. We know that it does not mean the concentrations are equal. We know how to look at a graph and determine where equilibrium occurs. Now, what I think they're wanting us to look at, so let's look at A plus B yields C plus D in an equilibrium system, all right? And let's just talk about what would happen if we increased. Let's go like this. Let's speak in code. The concentration of A is increased. How is that going to affect our rates? Well, if we have more of A, right, then we have more particles to react, right? So what is that going to do? That is going to increase the rate of the forward reaction. I mean, to me, this all just makes sense. And that's why, as I started, I was like, what do you want me to tell these kids in this topic? Right. But if I increase the concentration of A, I'm going to have more particles to collide, greater likelihood of effective collisions. I'm therefore going to increase the rate of the forward reaction. And because the rate of the forward reaction has increased, we are therefore no longer at equilibrium, right? Because the rate of the forward reaction has increased, but the rate of the reverse reaction has not. Okay. And what we'll see is we will see a net increase in the amount of products. Okay, that's cool. That makes sense to me. And that's what would happen if I increased either A or B, right? So we could write or B because both of which are reactants. Now, if we were to turn that around and we were to say that either A concentration or B's concentration is decreased, right? Then what would happen? We would have less particles. We would have less collisions. We would have less effective collisions. We would have a slower rate of the forward reaction. So what would happen there is, therefore no longer at equilibrium, right? Because we just messed up the rate of the forward reaction. And we would have right, the forward would be slower than reverse, right? Because we slowed the forward. Up above, when we increased A, we had the forward was faster, than reverse. Okay, because we increase the concentration. Now we have a forward is slower than reverse, and we see a net increase in products. No, in reactants. I'm sorry, because we're going faster in that reverse direction. So we have a net increase in the reactants. And when we could say vice versa, right? We could do this in terms of the change in concentration of the products. So if I had C and D, and we'll just do one, let's say that the concentration decreases, right? So we have less particles to react, to collide, right? Less collisions, slower rate, right? Less collisions means a less likelihood of effective collisions, slower rate. And then, so what we have is the forward is now faster than the reverse. And we see an overall net increase of what? You tell me, net increase in products. Okay, that's it. That's all I could figure out. Well, right on.